Donc nous allons commencer la dernière session de cette journée en hommage à Anatole Abragam. Et c'est mon grand plaisir donc d'introduire le prochain speaker, qui est Daniel Kleppner, et je vais le faire en anglais, puisque le papier de Dan va être en anglais. So it's my great pleasure to welcome you, Dan, to this session in honor of Abragam, and I thank you for having left Boston in the middle of Thanksgiving celebration to be here with us today. Dan is a professor emeritus at MIT, and we all know him and his work, so I will not be too long, but I will just recall that he has had a very long and fruitful career in physics, that he had made many breakthroughs in atomic physics. He invented the hydrogen maser in the early 1960s. He developed the study of van der Waals interaction between alkali atoms on atomic beams, and he measured with a very high precision the magnetic moment of the proton, and he made pioneering studies in Rydberg atoms, and finally he was a pioneer of Bose-Einstein condensation. In the late 1970s, he started an effort to condensate hydrogen atoms, and this led to the whole field of Bose-Einstein condensation, which has had tremendous applications and developments over the last 20 years. So, I really wanted to emphasize that, and Dan will talk to us about the roots of Anatole Abragam's science, and let you the stage.
Well, thank you, Serge. I feel very honored to be invited to participate in this reconnaissance of Anatole Abragam. I apologize for speaking in English, but I would have to apologize even more if I attempted to speak in French. What I want to talk about, or what I was asked to talk about, is the science that preceded Abragam, the science on which he built his career. A few years ago, I was asked to give a talk at a memorial session for Norman Ramsey, and I wanted to make the point that his book on molecular beams was what we call the Bible of the field, so I took a snapshot on my shelf of the molecular beams. And I noticed right next to it is Abragam's The Principles of Nuclear Magnetic Resonance, because that also is a Bible on my shelf, and I've used it for many, many years. So in this sense, I know Abragam for a long time. Personally, I've only met him a few times, and they were always very pleasant meetings. He is such a charming and interesting, and to me, a very warm person. So I have very pleasant personal memories of him. Just to show that this is really a classy group of Bibles, on the left it is Landau and Lifshitz, and on the right it's Bethe and Salpeter. These are all classics, and certainly Abragam's book is a classic. So here's a picture that was in his autobiography in English, which is called Time Reversal. It is one of the great autobiographies in science. I think it is absolutely marvelous reading because of its scientific interest, and of course because of his great humor and his compulsion to tell tales, which just give the book a special animation, which I think is characteristic of Abragam. I've puzzled over this picture. It's a wonderful picture. First of all, he's contemplative. He's looking, thinking about something or somebody, and perhaps smiling a little bit about it. It's hard to tell exactly what. I've concluded, at least temporarily, that what he was thinking about was the photographer. Is this going to be a good picture or not? But in any case, I think this captures his personality in a very special way. Now, Abragam saved me a lot of work because he explained exactly how his work got started. He pointed out the roots of the work in his autobiography. Said, I discovered NMR in 1950. To those of you who think that it was Bloch and Purcell who discovered it 4 years earlier, I must explain, and he goes on to give an explanation of what he means, and it's slightly risque, so I will not repeat it here. But he does attribute his involvement with the field, his initiation into the field by that discovery 4 years earlier. Well, he said he discovered it in 1950. 4 years earlier was 1946. Here's what he was talking about. In 1945, the summer, the war ended. The scientists rushed back to work as quickly as they could. New results from these scientists, and I'm sure some of them were pent up from the war years, were presented at the first post-war meeting of the American Physical Society in Cambridge, Massachusetts, April 25th to 27th in 1946. That was an unusual meeting. Here are the abstracts of 10-minute papers. You may not be able to read them from your seat. So, B6, Nuclear Induction by Felix Bloch, W.W. Hansen, and Martin Packard of Stanford University. The next paper is a second one with the same title. Well, this was new science, and they felt that you needed at least 20 minutes to explain the principles of it and what they had accomplished. So they had 2 papers there. Felix Bloch, of course, is well known to everyone because of his work on the conduction of electrons in crystals, on Bloch waves. He was the person who laid the foundations of band theory. So he's a very distinguished theorist. He got his start with Pauli. He fled to Stanford in the early 30s because of the rise of Nazism. Martin Packard was a graduate student working with him who later became well known as one of the founders of the Hewlett-Packard Foundation, or the Hewlett-Packard Company. They've set up a foundation, but it's the Hewlett-Packard Company. And Walter Hansen was a very gifted electrical engineer working at Stanford who collaborated with Bloch. Hansen was the inventor of the klystron. And that invention at Stanford launched the microwave industry in California. And it was the microwave industry in California which laid the groundwork later for the semiconductor industry in California and the growth of Silicon Valley. So Bloch was working with very unusual people. Walter Hansen was a genius at electronics, and he met an early death, a very sad one. He liked to do his machining work himself, and he was machining things out of beryllium, and he died of berylicosis. He did not know, at the time it was not known, that beryllium was a fatal poison. Anyway, those are the two papers which introduced what was called nuclear induction. And then the next paper, The Theory of Magnetic Resonance Absorption by Nuclear Moments in Solids by Torrey, Purcell, and Pound from the MIT Radiation Laboratory. And the next paper on that is a continuation of the work, Measurements of Magnetic Resonance Absorption of Nuclear Moments in Solids by Pound, Purcell, and Torrey. Again, you need at least 20 minutes to introduce a revolutionary new idea, so they submitted 2 papers. What was interesting is that neither of them knew the other was presenting at the meeting. They met for the first time and were rather surprised that they had such similar ideas. And in fact, after some discussion, they realized they were identical ideas. They detected the signals in rather different ways. Pound, Purcell, and Torrey look at the absorption energy of the system, while the others, Hansen, Packard, and Bloch, looked at the induction of signals due to nuclear resonance. but they were just looking at the real and the complex part of the susceptibility of the system, and they quickly realized that it was essentially the same thing. And they had some discussion on what to call it. Should it be nuclear induction or magnetic resonance? They settled on nuclear magnetic resonance, so that's how the title began. Now, the paper is interesting. This meeting was interesting for another paper, too. That was B9. B10 is called Spontaneous Emission Probabilities at Radio Frequencies by Ed Purcell at Harvard University. That paper points out that the spontaneous emission of rate of nuclei, which are precessing, is enhanced if they're in a cavity, and namely that the spontaneous emission rate is changed by a cavity. Very interesting result. Purcell told me that after the meeting, Robbie came up and sternly lectured him against wasting his time on such a frivolous idea when there was such important new results to be talked about. Of course, this is the idea which launched the whole subject of cavity quantum electrodynamics, which has evolved so happily right here in the Collège de France. Well, that's just a little aside. Now, both of these people said that the origin of their work was the creation of magnetic resonance by I.I. Robbie. One doesn't need to surmise that. Here are the three people. This is Robbie at the time of his Nobel Prize in 1944, Felix Bloch in 1954, and Ed Purcell in 1954. In Bloch's Nobel Prize lecture, he makes a very nice statement. It is a tribute to the inherent harmony and the organic growth of our branch of science that every advance in physics is largely due to the developments that preceded it. The discovery for which Purcell and I have received the honor of the Nobel Prize Award for the year 1952 is a typical example of this situation. Without attempting completeness, I want to mention some aspect of Robbie's method in the brilliant series of investigations which he carried out with his collaborators. The most significant improvement in molecular and atomic beam techniques was the introduction of the magnetic resonance method. So Bloch agrees that it was Robbie's invention of not nuclear magnetic resonance, but magnetic resonance in molecular beams that gave him the thought to move in this direction. And this is also true for Purcell and his group. It was Purcell and Pound and Torrey who reported it, and in the memoir on Purcell by Bob Pound, he wrote, the concept of nuclear magnetic resonance in molecular beams had recently been highlighted with the award of the 1944 Nobel Prize for Physics to our colleague I.I. Robbie for his pre-war research. So the origins of Abragam's interest in nuclear magnetic resonance goes straight back to that discovery by Robbie of molecular beam magnetic resonance. So what I want to do is talk about how that came about. What were the origins of it? Now, this is an abbreviated chronology. It's a very interesting story. I'm just going to give some of the highlights of it. And it really started for our purposes with Otto Stern's laboratory at Hamburg, where he started doing experiments on gas kinetics. From the modern point of view, these were rather old-fashioned experiments. He wanted to measure the speeds of molecules in vacuums. But actually, in his Nobel Prize speech, this is the aspect of it that he emphasized, what he called method of molecular arrays. And the idea is simply to have a source of atoms streaming into a vacuum to collimate them into a beam, and then use them for different things. Well, one thing that he did was to measure the speeds of atoms. And the way he measured it, well, there are several ways you can do it. You can do it with a toothed-wheel chopper, but he found it was actually more accurate just to let them fly a few meters horizontally and measure the displacement vertically. The very fast ones don't fall very far, going 2 meters. The slow ones fall correspondingly further. And this curve down below here shows his measurement of the speed distribution of molecules. It was the Maxwell-Boltzmann curve that he was looking for. Actually, what he found was rather puzzling. At the lower speeds, the curve does not increase as v squared, but as v cubed. And he was very worried about that, but then he had a happy visit at the laboratory from somebody who had a good deal of insight into nature, Albert Einstein. And Einstein pointed out that what he was not measuring the speeds in the gas itself, but the speeds in the beam. And the faster ones get out quicker. And that increases the distribution by one factor of v. So that settled that question. But there's an even more interesting aspect to this curve, which seems to have been done very carefully. This was done a few years later by Stern and Esteman. If you look towards 0, you notice the curve doesn't go to 0. It doesn't start out as v squared or v cubed, just seems to cut off. And careful measurements will show that's the case. And the reason is that in an atomic beam, very slow atoms get scattered out by the very fast ones coming from behind and hitting them. So that's a little detail of the measurement, but it turned out to be a very important detail because some years later, Zacharias at MIT attempted to build an atomic clock which made use of the very slow atoms, the fountain clock, where atoms shot up into the air and then the very slow ones would fall back down and give a very narrow resonance curve. And after working for some years, they realized that there are no slow ones there. Well, the data was all there in Esteman and Stern. Okay, the big advance, of course, and Stern's real contribution was his magnetic deflection experiment and the discovery of spatial quantization in 1924. That's just the paper which announced it. And this is from that paper. On the left, we have a source of silver atoms. You have a slit. You have what he calls a deflecting magnet, and then the detector, chemical. And this is a picture of the magnetic pole pieces. It's sort of a classic design now to give a very inhomogeneous field. And then in the inhomogeneous field, there is a force on a dipole magnet. And the atoms go through, have magnetic dipole moments. They get pushed one way or the other. And by classical physics, they would get pushed equally one way and the other. By quantum mechanics, there are just two states, and that's a picture of the trace. That's from the paper. I've seen many copies of this experiment purporting to be the data of Stern and Gerlach, but actually the data is much clearer here than in any of the copies that I'd seen. But it's quite clear that that line is split. And that split had huge repercussions. It forced people to take quantum ideas seriously. In particular, it had a big effect on Pauli, who, well, everyone in 1924 was uncomfortable about the situation of quantum mechanics, and this sort of called it to a head. So this was really an epoch-making experiment. Now, something else very interesting happened in 1924. Pauli proposed that nuclei have spin and angular momentum. He proposed this in order to explain hyperfine structure, and his explanation worked out beautifully. The puzzle about this is the following year when Goudsmit and Uhlenbeck proposed that the electron has spin. Pauli was fiercely opposed to it. He could not accept the idea. He actually tried to block them from publishing, but he was too late. So their letter went off without his blessing. He just didn't think that electrons could have a spin 1/2, but he was quite happy that nuclei could have spin of arbitrarily large size if needed. Well, I just mentioned that as a rather curious incident in the history of physics. Okay, that same year, Rabi, who was then 26 years old, started studying at Columbia University. And someone there was on the ball enough to tell him that he ought to give a seminar on the Stern-Gerlach experiment. So he looked into the experiment and he became hooked on that. And this sort of set the direction for his career. He got his PhD a few years later and immediately went off to Europe, because at that point, the US was a total scientific backwater, and Robbie had the instincts that Europe is where all the action would be. He just went. He didn't have a fellowship. He just went. He went to Copenhagen, and he went to the Bohr Institute and knocked on the door, literally, and the secretary came, and he explained that he'd come to study physics with Bohr. And she said, "Come in." And Bohr was away on vacation at the time, so we had an office until Bohr got back, and they started talking. And Bohr decided that that Robbie wasn't cut out to do theoretical physics at the Bohr Institute. But it didn't end up so badly. He arranged a fellowship for him to go work with Pauli. So he went off to Hamburg and started working with Pauli. And Pauli suggested that he look into the effect of the Dirac equation on the motion of free electrons. So Robbie looked into that, worked some time on it, and he found, to his disappointment, that there was really nothing new there. And so he was feeling rather distressed. But he did happen to bump into Stern and start learning about Stern's experiments that he'd already known about, of course, earlier. But they started tossing ideas back and forth. And Robbie tossed an idea to Stern, which Stern said, "Why not try it out? Come on down to my lab." He gave him laboratory space and support. And Robbie then turned from a theorist into an experimenter, which I guess just shows how easy it is to buy off a theorist. Just give him good experiments to do. Anyway, from that point on, Robbie was basically an experimental physicist. And he worked in the laboratory, and he did a rather ingenious experiment. It was called molecular refraction, as distinguished from molecular displacement. It depended on deflection in a uniform field. And this little diagram shows what will happen if you have an atom go into a magnet, a uniform magnetic field. If its energy depends on its state, the two states are going to be accelerated slightly differently. And it's just like a light going into a dielectric, into a solid with a refractive index. So the beam will split. And this potentially would give you a way to look at the magnetic states of the atom individually. So that's what he worked on there. He didn't actually carry out the experiment there, but the following year he went to Columbia University. He got a position in Columbia which was very unusual. Columbia was notoriously anti-Semitic, as were most American universities at the time. But Heisenberg had paid a visit to Columbia the previous year and talked to the head of the physics department, Pegram, and said that he thought that Robbie was terrific and they ought to grab him, and they did. So he went and set up a laboratory at Columbia University and started a research group and spent the rest of his career there. In 1931, Bright and Robbie collaborated on this energy formula, which is well known to everyone who works in this branch of atomic physics, the Bright-Robbie formula. It shows the energy levels of a spin 1/2 system, an atom with a spin 1/2 electron, and nuclei of any spin that you like. The top level is nuclei with a spin 1/2. That would be hydrogen. The lower level is for nuclear spin 3/2. And Robbie did these experiments that I showed, the refraction experiments. And what you do is you turn up the strength of the uniform magnetic field. And as you turn it up, first one, then another of these beams hits the detector, and just by counting peaks, you know the nuclear spin, and that's how the first nuclear spin measurements were made. Robbie was delighted with the method. One thing about the method is you can improve the sensitivity just by making your uniform field longer and longer, because you get larger and larger splittings. So he was very consumed with trying various forms of molecular beams for making measurements. The interest was in nuclear physics, in the spins and magnetic moments of nuclei. So the following 4 years, they've tried various geometries to improve the sensitivity and signals from molecular beams experiments. The top one shows a diagram in which atoms will get through to the detector no matter what their initial direction is. The ones which go close to the axis in the first magnet, it's two deflecting magnets. The second one will bring them back. And what is also shown in this diagram is a middle region called the C region. If anything changes the orientation of the spin in that C region, then atoms which got to the detector previously will not, because they'll be deflected the wrong way in the Stern-Gerlach field. So this was in the works. They were using this. They were making measurements of nuclear spins. They could never measure the magnetic moments very accurately with this method. Robbie concluded that the best you could ever measure was 10% using deflection methods. Then Robbie got interested in the problem of trying to find out the sign of the magnetic moment. These deflection methods will tell you the size of the nuclear spin, but it won't tell you whether the magnetic moment of the nucleus points along the spin or in the opposite direction. So this became a very real problem for them. And he started thinking about various geometries which would be sensitive to the spin of the nucleus. In particular, the one on the left, the T field, is a field which, if the atom passes through it horizontally, the field rotates as it goes through. It rotates and it changes directions. The atom would have to make a non-adiabatic transition in the center, but by knowing which direction you wanted to rotate to make that transition, you could tell the magnetic moment. Well, in 1937, in March, Robbie wrote a paper, one of the very few papers he wrote, but this was a paper giving the theory of this experiment. It's called Space Quantization in the Gyrating Magnetic Field, and it was submitted in March 1937. A few other things happened that year. In that fall, a visitor came to Columbia, and the visitor was Cornelius Herter. And Herter told Robbie about something he'd been working on, and he showed him a paper called Negative Results in an Attempt to Detect Nuclear Spins. He was trying to look at nuclear magnetic resonance in a solid without success. So this was maybe the first attempt to detect nuclear magnetic resonance. And if Herter's experiment had worked, he would have been the one to be recognized for that. He suggested to Robbie, why don't you use my method? I use an oscillating field. And Robbie immediately saw that this was exactly what he needed in that C region. His T field is a very crude thing. The field rotated at most sort of 1/2 cycle as the atoms passed through, and the speed of rotation depended on the speed of the atoms. If you put an oscillating field on it, you can make the field oscillate as many times as you want, and it's independent really of the speed of the atoms. According to Ramsey, who had joined the group that fall, that Herter had made that suggestion, and he made it on the day he was leaving, which is a Saturday. And Robbie immediately saw this was the way to do it. And the following Monday, they started changing the apparatus around to look for magnetic resonance. So the result, well, here it is published a year later, the molecular beam resonance method for measuring nuclear magnetic moments by Robbie, Millman, and Cush, and Zacharias. Ramsey was just a fresh graduate student, and he came too late to work on that experiment. And the experiment has this beautiful diagram showing the atoms passing through the field, showing the direction of the precession at the top and at the bottom. And it shows the apparatus. And it shows a beautiful, what we call a Robbie resonance curve. This resonance curve was actually apparently described in Robbie's paper on gyrating magnetic field. I've looked at the paper, and it's really very difficult to extract the resonance curve from it, but I understand that you can. The reason is that he was looking at a totally different system with a field which could rotate at most pi radians and depended on the speed of the atoms. But anyway, that was the birth of magnetic resonance. Now, that laboratory flourished for many years. All the research was interrupted by the war. But in those pre-war years, there were classic experiments carried out. One was, in fact, probably the most important experiment, was the discovery that the deuteron has a quadrupole moment. And that came about almost by inadvertence, because that was actually made by Norman Ramsey. There were two labs at Columbia. There was one on the 5th floor and one on the 10th floor. The 5th floor used alkali halide molecules, lithium fluoride, lithium chloride, and things like that. And the reason is that those atoms could easily be detected by having the atom hit a hot filament and then it ionized, and you could measure the current. The top floor, this is a more serious floor, is where they were working on hydrogen and deuterium. And the problem, there were two problems with hydrogen and deuterium. You do this with molecules, H2 and D2, and you deflect them by forces on the nuclear moments, which are much smaller. So you have to have much higher deflecting power and much higher spatial resolution. That's one problem. And the other problem is that these gases are very difficult to detect. At the time, they used what was called a Pirani detector. You let the atoms go through a slit into a chamber, and the pressure went up a little bit, and you could measure the pressure in there with a sort of a hot wire manometer. Anyway, they were trying the resonance on HD molecule and getting nowhere at all with it. It worked beautifully the first time with the alkali halide molecules, but it was just a mess upstairs. And what the group decided was it was working so nicely on the alkali halide molecules, they didn't want to waste their time in this machine upstairs. So they gave the problem to the youngest person in the group, which was Ramsey. Said, why don't you see what you can do with it? And so he went to work himself on the machine, working at nights with it in order to make use of the battery, which was shared between the labs. Anyway, he started tinkering, as a good experimenter does, and what he discovered was that they were just putting too much radio frequency power into it, and if you turned it down, you got better signals, and they got better and better. Finally, he got beautiful resolved signals, and the resolved signals had sidebands where they were not predicted to be at all. This is in the HD system, and that was immediately recognized as an indication that the deuteron has a quadrupole moment. At that point, Norman says the experiment became very hot. Everyone rushed to do that. He was going to do that experiment for his PhD because at Columbia, you had to write a paper all by yourself on your experiment. It had to be published in something like 100 copies, which meant that it had to just be published. But you weren't allowed to have co-authors. And he agreed himself that this was too hot to give to him for his PhD experiment. And he got his PhD easily on something else, but the whole group pitched in, and they announced this discovery of the quadrupole moment of the deuteron. The following year, there was a follow-up paper on it, and that follow-up paper gave reference to 10 theoretical papers trying to explain the deuteron quadrupole moment by people such as Bethe and Wigner had been working on this problem. Schwinger had worked on the problem. So it was a major discovery, and this was a major step forward in that laboratory. So the laboratory became well placed on the international scale of things, and it was a tragedy that it had to stop because of the war. Basic research stopped because of the war. Right after the war, the physicists got back to work as quick as they could. In September of 1945, Ramsey, who had been at Los Alamos, left there and returned to Columbia to help Robbie rebuild the laboratory. Purcell had been working at the radiation lab at MIT, where they developed radar. And it was felt when the rad lab closed that the work there should be properly documented and preserved. And it has been in a series of books called the Radiation Lab series. And one of these books is Montgomery, Purcell, and Dickey. That's the basic text on microwave electronics. It's the one that I used when I was doing microwave work, and lots of people did. These are classic books, and they were written by people who stayed on instead of rushing away that fall. They were continued at the rad lab, and Purcell was one of these. So all day long he was writing this book, but the evenings he had to himself, and there was lots of equipment around in the rad lab, and it was during that period that he did these experiments with Pound, who also worked at the lab. Pound was a expert on microwave detection, and that's when the experiments got done. So that's how Abragam's work got started. Those were the foundations for his work. Now, it's hard to estimate just the implications of this work. We've heard some of them this afternoon about the NMR work going on. But the development of lasers, for instance, the development of quantum electronics were all influenced by this discovery. The spirit of the discovery was eloquently expressed by Ed Purcell in his Nobel Prize lecture. He wrote, "I remember in the winter of our first experiments just 7 years ago, looking on snow with new eyes. There the snow lay around my doorstep, great heaps of protons quietly precessing in the Earth's magnetic field. To see the world for a moment as something rich and strange is the private reward of many a discovery." So it's a really eloquent description of why it's worth doing science. I'd like to digress in the spirit of Abragam and tell a story which is totally irrelevant to this incident, but also reflects on Purcell's character. In 1951, Ed Purcell was the first person to detect the 21 centimeter radiation from hydrogen in space. This started the whole subject of radio astronomy of hydrogen, and that was an advance of incredible importance. Right now, they're using the techniques which evolved from that to look at the energy density of the universe in its earliest stages, when the atoms are so far away, moving so slowly, they're barely detectable, and the radiation is no longer 21 centimeters, but some meters. That experiment was done on the roof of the Lyman Laboratory by Purcell with a graduate student, Doc Ewan. They put together a simple microwave receiver and just did the experiment very, very carefully, and they saw it. Purcell knew that there were others looking for it, in particular Jan Oort in the Netherlands was about to detect it. They had been in contact with each other. And Purcell held up his publication until Oort found it also so they could publish side by side. The publication was, turns out, was held up almost a year, but they published side by side on that because Purcell thought that was the right thing to do. So Purcell was in every sense an elevated person, and this is what Abragam had to say about him. As a physicist and a human being, Ed Purcell is perhaps the man I admire most. I have never met anyone with more profound, authentic, more detached from the wish to appear other than he is. And that is a very pithy, accurate, and moving description of Ed Purcell by Abragam. Abragam had this ability to really understand people and to understand what was best in them. And I think it was wonderful that we had Ed Purcell to do his work, but I think it was wonderful that we have Abragam's heritage now, not only of science, but of his views on science and the effect that he's had, the impact on those who've come after. So, thank you.